Hi everyone. We will start our class now. My name is Jiyoung, and today I'm going to introduce you how to build autoencoder with using PyTorch. Before we start, make sure that you change your runtime with using the GPU, T4 GPU here. So in this session, we aim to familiarize ourselves with autoencoders, a special type of neural network architecture. We will also dive into a variant known as the denoising autoencoder. By the end of this session, you will understand the basic architecture and functionality of an autoencoder, implement a simple autoencoder and visualize its latent space, and modify the autoencoder to create a denoising version. First, we will now import the required libraries. Then we will set hyperparameters. For this session, we will set batch size of 256, learning rate of 0.0002, and number of epochs of 10. Today, we will use the dataset called MNIST. So first, we have to download the dataset. So we will download the train dataset, the MNIST for train dataset, and test set for MNIST. And after downloading the train dataset, we will randomly split the train into 50,000 to 10,000 into a training set and for validation set respectively. So when we check the dataset, one sample for the input sample has a shape of 1 by 28 by 28. This means that the image in MNIST has 28 by 28 pixel sizes. And when we look at the label, it has only numerical value of 1. So it tells that this a particular sample is an image of a 1. Next, we will make data loaders. And when we check the data loader for the train set, it has 196 samples in the train. Now we will build our own autoencoder. So in this case, I will build a autoencoder that first linearizes the input of the image and shrink it to 100, 30, and then expand it to 100, and expand it to 784, which is the product of 28 by 28. So first, for the encoder in the autoencoder, since the input itself is the linearized version of the input dataset, it will be the first dimension of the linear layer will be 28 times 28. Then, since we decided to shrink it to 100, the second parameter for the linear layer will be 100. Next, we will add an activation layer, and in this case, I will just put the ReLU layer here. And for the second linear layer, since the output of the first linear layer is 100, it will start with 100. And we decided to shrink it to 30 again. And after the linear layer, we will add additional activation function, which is identical to the above as ReLU. And then for the decoder, since the output dimension of the encoder is 30, it has to start with 30. And we decided to expand it to 100. So the second parameter for the linear layer will be 100. And again, we will add an activation layer, and I will use ReLU again. And for the second linear layer, it has to start with 100 since the output of the first layer is 100. Then the second parameter for the linear layer should be 28 times 28 since we have to match with the input size. And lastly, the last activation function for the decoder will be sigmoid here. So this is our autoencoder. And for the forward section, it will get an input of X, which is the batched images. So for the batch size, we can get it from the first dimension of the size function. Then before the images goes into the autoencoder, it has to be linearized. So here we will linearize with using the view function of first parameter of being -1 and the second parameters of being 28 by 28. So it will be identical to the batch size, identical of shape of batch size by 28 by times 28. After that, the input image will go through the encoder. So the encoded will be self.encoder of X. Then the output will be, it first has to go through the decoder. Then we again have to make it to the original shape of batch size by 28 by 28. So this will be our autoencoder. Now we will train our autoencoder with using MNIST dataset. First, we will identify the device, whether it is GPU or CPU, and initialize model with using autoencoder, and then move to this model to the device. And we will use loss function of MSE loss by specifying it by nn.msE loss. And for the optimizer, we will use Adam optimizers. No, sorry. There is a typo here. Void. Now we will build a function to train the model. So this train function here, I made train loss history and valid loss history as a list, and I will stack the loss as we train on to this list. And for the best model weights, I just copied from the very initialized model weights, and I will replace it whenever the loss gets the best performance. And for inside the for loop, we will train the model as the number of epochs we set the above. So during the train phase, the model has to be set as a training mode. So we will do this by writing model.train. And during the evaluation mode, the model has to be set as the evaluation mode. So we will do this by setting model.eval. And for this running loss, I set this to calculate the overall loss for one epoch. And now we will iterate over data set. So we get the inputs and the label for the batch size. First, we have to move the input images to the GPUs. So it will be inputs to device. And before we start training, we always have to zero the parameter gradients. So to zero the parameter gradients in the optimizers, we have to write optimizer dot zero grade. And during the training, we pass the inputs to the model, then it will give us outputs and the encoded latent space. So for the loss, since we decided to use the MSE loss and predefined above, the loss will be criterion of outputs and inputs. And if we train the model, we have to first backpropagate the loss from the model. So it will be loss.backward. Then after we perform backgradients, we have to do the optimizer have to change the model weights to minimize the loss. So that part would be optimizer does step. Then to calculate the overall loss inside the one epoch, we will multiply the loss by the batch size. Then after running all these mini batch sizes, it will be divided by the overall data set in one epoch. And here we track the epoch losses in the training loss history. And for the valid evaluation, the evaluation loss will be also tracked in the validation loss history. And whenever the evaluation loss is lower than the best evaluation loss, the best model weights will be replaced by the that particular model weight. Then now we will, with using the train function that we defined above, we will train our data set. So after running all these epochs, we can see that the training loss is getting decreases, even though it's very slightly. And also evaluation loss is decreasing, even though it's very slightly. Since we are only running the 10 epochs, so maybe if you run more, the loss will decrease like more dramatically. Then now we will plot the learning curve like below. So first, we will plot the training loss trajectory, which will be PLT plot of training loss history with label being train. Also, we will plot the validation loss history with using PLT plot validation loss history with label being val. The X label is the title of the X, so it will be epoch. And Y label is the title of the Y-axis, which will be the loss. Yeah. So first, the train loss decreases dramatically, even though we cannot really see the difference here, but we found that we saw that the exact numbers of loss is getting decreasing. Now we will check our pre-trained model with test images. So with using the test images, it gives us the loss of 0.067. Also, we will plot the images of the output of our model. Yeah, so if you train the model more, it will give more clear images of the input image and more similar images to the input image. So the left one is the input image and the right one will be the output of the model. Yeah, so if you train your model more, it will give more similar images to compare to the first image. Next, we will visualize the latent space of the autoencoder. First, we will bring up the model called Tinsney from scikit-learn. And we will pre-process the MNIST test dataset by dividing the values by 255 and move that values into the NumPy array. And here we move the test dataset input to the PyTorch tensor and move to the GPU devices. Then this test dataset goes through the best model. So it gives us the outputs and encoded, the latent encoded space. And to visualize the latent encoded space, it has to go down to the CPU and the gradient has to be detached and change it to the NumPy. And now we will initialize the Tisney by using the code Tisney. Then we fit the encoded latent space by using Tisney.fit transform. And with using min-max, we normalized the output from the Tisney by using the min-max normalization. The process of Tisney gets longer than I expected. So if you run this code and run this code to visualize the output of the Tisney, it will give you of this scatter plot, and each color represents each number, each sample that corresponds to the each label. Then to interpret more directly from this scattered plot, we can add the labels from each sample. So if you run this code, it will give us this scatter plotted, which is identical to the above, but it's more bigger, so it will look like scattered version of the above. And we can see that the samples with same colors are clustered to each other. For particularly the orange dots from here, where the samples are all with labels of 1, they are scattered together, they are clustered together. And for the 7s, the samples with gray color, they are also clustered like together. So we can see that even though there are some clusters that are divided into 2, like in this case zeros, but mostly samples with the same labels are well clustered to each other. And with using the autoencoder, we can implement another variant of the denoising autoencoder. Denoising autoencoder is a model that gets input with slightly corrupted with using noise, but the model has to output the cleaned version of the input. So we will use the identical architecture as we defined above, and we will also use the identical loss function, which is MSA loss for the loss function. And also, we will use the same Adam optimizer to learn it, but in this case, I will just set the learning rate of 0.0002 to facilitate the learning process. So the train function here is identical to the above, but the only changes that has to be is that before the inputs go through the model, it has to be corrupted with using very slight noise. So here we will make a random noise and then add to the inputs. So first we will make a noise of 0 vectors, but with the identical shape of the input. So the noise will be torch dot zeros, inputs of size of 0. So this means the batch size, and 1 by 28 by 28. So this noise here will be the 0 vectors, but the shape is identical to the input. Then we have to make the noise as the noise, not the 0 vectors. So here we will use the PyTorch init function with normal Gaussian of noise being Gaussian noise of being mean of 0 and standard deviation 0.1. So the code will be nn.init.normal underline noise, comma 0, comma 0.1. And after making this random noise, we have to move this noise to the GPU device, which will be done by noise to device. Oh, sorry, I missed some questions in the chat. So first question is any reason as to why we use sigmoid for the last layer? Also, can we just type 784 instead of 28 times 28? For the first question, there is no particular reason of setting the sigmoids for the last layer. That's just that's a choice of the developers. And also you can type 784 instead of 28 by 28 times 28 since they are identical. For the second question, what's the learning rate set to 0.0002? Yes, for the above model, the learning rate was set as a smaller number than this one, which was, I guess, oh, sorry. So it's identical. I think I confused. So yeah, it's identical. The next question for making the noise of making torch zeros, input size 0, 1 by 28 by 28. Um, the input size of 0 is the batch size, and the 1 is just additional dimension. So originally what happens in the image data set is that the MNIST data set, it's only like black gray images, but for when it comes to the color images, it has the pixel values for each red and blue and green. So for the color images, the second place for 1 will be changed to 3. But for MNIST, since we don't have that RGB values, but only just like black, how black it is, so it is just 1 in our case. For the next question, so your scatter plots looks quite different. Yes. So for this scatter plot that I prepared for this session is that I trained the model more than this our session. So it will give more like accurate and more pretty figures than you. So if you train your models like for longer epochs and if you tune your hyperparameter more, then it will give like nicer scatter plot than the one that you posted in this chat. Yes. Also, just like CNN. Yes. So CNN also has channel sizes, but they, yeah. The CNN, I guess the CNN like mostly starts with channel size of 3, which corresponds to RGB value. So yeah. So that's kind of the same concept. Okay. Now, uh, yeah. So after making noise, we move the noise to the GPU. Then next, we also have to move the inputs to the GPU, which can be done by inputs to device. After that, we will make noise inputs, which is the addition of inputs and noise. So it will be inputs plus noise. And the remaining section is identical to the above. So if you look at the loss from training and validation respectively, even though very slight changes, but still it decreases. So if you run longer, then it will give you the better results. Next, we will plot the trajectory of loss functions for the denoising autoencoder. So first we will plot the training loss by using plt plot.train loss history dash d with label using train. Next, we will also plot the validation loss with using plt plot val loss history dash d with label using val. The title of the x-axis will be epoch, and the title of the y-axis will be loss. Yeah, so even though it looks like similar to the above, but still it is decreasing. And when we test our trained model on the test set, will give us loss of 0.06. And when we visualize the output of the denoising autoencoder, for now, since the data is not well that trained, yeah, it will give us not very clear images. Oh, sorry. The comment from Hitan is right. I made a mistake. So when we build our model, in the for function, the input shape should be identical to the input size. So the output of the decoder should be the batch size by 1 by 28. Yeah, maybe that's why we couldn't really reproduce the out result. Then after fixing the model, maybe we can rerun just for the denoising autoencoder here. Yeah. Rerun the denoising autoencoder here. Yeah, then if we replot the loss trajectory for training validation set, yeah, it will give us a nice figure of decreasing the loss function. Yes, the correct code for the model forward function is this reshaping the output by batch size by 1 by 28 by 28. Yeah, sorry for the mistakes. Then the test loss, the loss for the test set, it gives us a 0.024. Then next, we will check if our denoised autoencoder works properly for the test set. So first, we get the output of the test from by when we calculate the test loss above. So with using this output images, like the reconstructed images from the denoising autoencoder, we are going to show how the test images reproduce. So for the samples up to with number 5, we first select the corresponding noise input of 1 and downgrade it into CPU. Then we will also show the output image of the corresponding input. So the left image is an input that is given to the model, denoising autoencoder, and the right image is the output of the denoising autoencoder. So we can see that the difference from the input from the autoencoder above is that like even like for the just normal autoencoder, the input images are very clear and the backgrounds are like completely black. But since we added Gaussian noise to the input, the background of the image is not completely black. So it is a little bit blurry, but still the images are identifiable since we didn't really add like much noises to the input. So for the denoising autoencoder, because the main objective of denoising autoencoder is to remove the noise and reconstruct the only clear version of the input. So even though the input images are slightly corrupted with using Gaussian noise, the output of the models are still clear images with background of being completely black and only the digits parts are white, so we can more clearly identify the digits. So this is the end of our practice session. So do you have any more questions? Yes, you can take your time. The question is, could you please explain a little bit about the choice of activation function in encoder and decoder? So the activation function is like really up to you. So there is no gold answer. And there are many other alternative to the activation function than the ReLU that I used here. But the reason why I chose ReLU is that it is the most popular activation function and most like many people use it for a long time, and that's ReLU is like the very basic of the activation function. So that's why I use ReLU for here. And there is no particular reason I use for sigmoid for the loss. So it was very my like design choice. So you can change it to anything that you want. Oh, and for the last sigmoid function here, since the sigmoid like gives us values between 0 and 1 that matches with the values to the input image, which is like very critical in our situation because we are calculating the MSE loss between the input and the output. So if the numerical value range between the input and output does not match, then it will like cause many big problems. So that is why I chose sigmoid for the last activation function. Yeah, so while we're waiting for people to writing their questions, I will explain more about what T-SNE is. So T-SNE is typically a visualization, is a dimension reduction function. And although these dimension reduction functions are used in diverse purposes, but one of the main purposes of using this dimension reduction is to visualize the latent space, so we can like see how the latent space are shaped, even though that's are not accurately represented. But since we can just like get how the represents are, just get the feelings of how represents are clustered, like which samples are clustered to each other. So after initializing t-SNE with using function t-SNE, we will feed the encoded latent encoded vector into using t-SNE dot feed transform. Then it will give us the value of each samples according to the like each dimensions. So first I normalize it the output of the t-SNE with using min-max normalization. And although the t-SNE gives us like multiple axes, the first axis is the most important one, and the second axis is the next important one. So the earlier the axis is, the more important feature it contributes to doing the dimension reduction. So that is why I use the first axis and the second axis. Okay. One another question. Beth, with using the function of train model, there is no variable with the name loss function, but the model somehow knows which one is the loss function. With the loss function, but its name is loss, not loss function. So I'm a bit confused. Hmm. The loss function here indicates, oh, sorry. Yeah, so loss function here indicates loss function here. So it's nn.msli loss. And we give this function as this criterion here. And it is used to calculate the loss in this. Mm. Does it make sense? And for the next question, loss, yeah, that's actually the response to the above question. Regarding your response does not match about sigmoid function, if you choose other function rather than sigmoid, we will get decreased accuracy. Maybe because the values for the input are between 0 and 1. And if we choose activation function of the value, then it can give us a value of like 100, which is not possible for the input. Then, if we directly calculate the MSE loss between like 0.6 and 100, then it will give us a bigger loss function. So that might not be what we want the model to be trained. So if you want to use other activation function than sigmoid for the last layer, then I believe that you should also post-process the output of the model to match the numerical value range between the input and the output. So next question is, so loss function goes into the place of criterion, so can I name criterion as loss? So this is just name for the variable, and I just put the criterion for the loss function here, and this criterion is used to calculate the loss. Yeah, so for the first question, loss function goes into the place of criterion because this is a Python function. So criterion is just the name of the argument. And for the value of the argument, I just put it loss function. And for the second question, so can you name criterion as loss function then? Yeah, it's a name of the argument, so you can name it whatever you want. So it can use as loss function, but make sure that you also change the variable name here also. So we will wait 5 more minutes just in case if there's anyone who is typing their questions. Another question, if we want to try practicing running the code with a different data set and use this set cipher10 instead of denoting, is there anything we need to consider? Oh, denoising. Code with different data set and use. What do you mean by using cipher10 instead of denoising? Cipher10 is dataset and denoising is a model architecture. So you meant using cipher10 dataset instead of MNIST. The first thing you have to, if you want to use the identical model architecture as just using fully connected layer as we done in our session, then the model architecture itself, yeah, maybe you have to change this the number of parameters inside the linear layer. So the first parameter of the linear layer would not be 28 times 28 since that may not match with the image size of the cipher 10. Then if the cipher 10 is bigger than this MNIST, then the second parameter should be also be bigger because if we shrink like the bigger than 28 by 20 times by 28, then 100, then the information loss will be greater than what we practice in our session. So you have to change the parameters of the inside of the linear layer. And also, as I mentioned, I recall that cipher 10 is a color image, so the number of channel wouldn't be 3, not 1. So you also have to consider like these other differences. So yeah, so you may have to change this. Yeah, you may have to consider that the channel size is different and the image dimension size itself is different. So maybe you can like alter the model architecture. Yes, you can see the code of adding noise part. It's uh, here. Yeah, we will wait just until like 11:27. One more minute. Yeah, I guess so. Yeah, another question. Regarding the previous question, I think process of autoencoding would be appropriate since MNIST and Cipher has the same number of classification. Um, but sorry, but autoencoder is not related to the classification. It's related to reconstruction of the input image. So if you recall the training processes, it calculates the MSA loss between input image and the output image. So the label is not really being used during the training. So for the Songok's question, then we can consider some structure of image between number and object. Yes, we can do that since the label spaces are different between the MNIST and Cipher10. Yeah, you can take your time to like type your question and your opinion. Yeah, we can definitely consider the some structures of images because we have like different images of like different objects. So yeah, that might be helpful when using the autoencoder when training autoencoder using the Cipher 10. Yes, as you mentioned in the question that you guess the different shape would affect the compression regarding autoencoder. That is true. So that is why I suggested um I suggested to change the hyperparameter between the linear layers so that um there might be more proper parameter than 100 for in case of cipher 10. Yeah, so I can we can wait just for one more minute just in case if there's anyone like writing their questions. Yes, the change in parameter value in case of either MNIST or Cipher is important. Yeah, since that's just design choice and nobody really knows the very exact proper value for each data set. It's we have to like do it and see the results. Yeah, so I guess everyone's questions is resolved, so we can like end session right now. So thank you for joining today, and I hope you have a nice day and nice weekend, and maybe see you next time. Yeah, thank you everyone.